morning. Let's start with the assignment 2. Let W1, W2, W3 up to WR generate a subspace of W of a vector space VF. Now a vector space VF is given to you, and also there is a subspace known as W, and this subspace is generated by W1, W2, W3 up to WR. These vectors, okay? Then there exists a subspace of W1 up to WR, which is a basis for W, right? What we need to prove that there exists a subspace of these W1, W2, right? Which forms the basis of this W, right? Okay, now because W1, W2, W3, these generate W, right? So if these are linearly independent, then these W1, W2, W3, these are the bases. If suppose these are linearly independent, then these are the basis for W, our work is done. Okay, if not, suppose these are not linearly independent, then there must be some Wi. There must exist some Wi, which is a linear combinations of the remaining W's. Or you can say WJs. Yes? Okay. So let me remove this Wi from the set then. Right? See, again I'm repeating. Suppose W1, W2, W are linearly independent, then our work is done because these are already the generators of W, and if these are linearly independent, our work is done. These forms the basis of W. Suppose these are not linearly independent, which means there exists some Wi, which is a linear combinations of the other Wj's. Let me remove that Wi, right? Suppose I remove this Wi. Fine. Now, if these are linearly independent, then these forms a basis for W, right? If still not, okay, what is remaining if I remove Wi? These are remained. W1, W2, W3, Wi minus 1 up to WR, right? So if these are linearly independent, our work is done. But if not, then again there must exist some Wi, which is the linear combinations of the remaining Wj's, right? Okay, so I'm starting this proof. If W1, so we go like this, right? Okay, let me start. If W1, W2, WR, these are linearly independent, then these forms basis for W. Fine. Okay. If not, if this is not linearly independent, then there exists some Wi, which is the linear combinations of the remaining vectors Wj's. Suppose this is your Wi, right? Now on removing this Wi, suppose I remove this Wi, we still get a generating set, right? And what is that generating set? W1, W2, so on, Wi minus 1. Now I have removed Wi now up to WR. Now if the set is linearly independent, then it is a basis for W, okay? Still, but if it is not, right? We repeat the above argument, continuing this way. There again exists some Wi minus 1 or Wi plus 1, which is the linear combinations of the remaining ones. Then we remove that thing. So we go on continuing like this. So we will get a generating set for W, right? In less than R steps, which is linearly independent. Because total number of W's we are having from W1 to WR, right? So we need a generating set. right? So we need a subspace of these which forms a basis for W, right? So we have a generating set for W in less than R steps, because from W1 to WR we remove WI. Then in the next step we remove WI again, or WI plus 1. We remove 1, 1, 1, 1 WJs among all the other WJs, right? Similarly, going like this, finally we will get a generating set in less than R steps. So which is linearly independent. So this final step will be the basis for W. At certain step we may get this generating set for W which forms the basis for W, right? This is just a simple concept to just know about the concept. And the remark is, please notice this is very important. If the number of equations is strictly less than number of variables, how about that? Suppose the number of equations, suppose I'm having number of equations as 3, right? And I'm having 4 variables in each equations. In a set of homogeneous systems of equations, so if the number of equations are 3 equations and the number of variables are 4. So if the number of equations is less than number of variables, then the system of homogeneous equations, linear equations, has a non-trivial solution, right? And non-trivial solution means determinant equal to 0. When you take the coefficient matrix, that determinant is equal to 0. Okay, so let's